Good afternoon, everybody. Welcome to ACI PBR session. My name is Minako. I'm a technical marketing engineer, part of Cloud Networking Business Group. That is a business unit producing Nexus 9K and ACI. I've been working on ACI almost from the beginning, especially working on layer 4, layer 7 integration in ACI. That is the focus of this session. We probably don't have enough time to take care of a lot of questions. So if you have many questions or complicated questions, please join WebEx space and leave messages. I will take a look at later. And I have many busy slides explaining forwarding and zoning rules. So I would recommend come closer to me or open up some document. You can find it on the WebEx app. Session objectives. After this session, I hope everybody understands the PBR use cases. What's the benefit and when to use PBR? That's objective number 1. Objective number 2 is I want you to understand how forwarding works. What's actually happening inside of the ACI fabric. That's objective number 2. And then I want you to understand what's the design considerations that would be required when it comes to applying PBR design to your network. So these are the session objectives. We are not going to cover cloud ACI in this session. We are focusing on on-prem ACI, including multi-site, multi-port, and remotely. The assumption is you already know what ACI is. This is a level 3 session, so I'm not going to talk about the basics, such as what is bridge domain, what is VRF, what is L3 out, and so on. In this session, I mainly use ESG, endpoint security group, in the presentation, but it doesn't matter from PBR perspective whether it's EPG, ESG, or USEG EPG, except multi-site. Multi-site currently doesn't support ESG, so I'm going to use EPG when it comes to multi-location data center design discussion, but I mainly use ESG in the presentation, but it doesn't mean that you have to use ESG, but I just say EPG and ESG interchangeably. I just want to let you know that you can use EPG, ESG, USEG EPG as long as that option is available. PBR-wise, there's nothing different. So here is the agenda. We are going to talk about PBR use case first, and then talk about how forwarding and zoning rules work. And then commonly asked questions and advanced use cases. Then finally, I'm going to talk about multi-location data center design and consideration with PBR. So let's start with ACI PBR use cases. So what sort of situation can we use PBR? To understand this, the most important fact is PBR redirect is just one of the contract actions. I believe everybody knows permit contract, that is a default option. You can allow traffic between two different ESGs, EPGs, and so on. We have deny action and redirect and copy, which means as long as we can apply contract, we can use PBR, redirecting traffic. So let's recap what contract is. Contract is based on source, destination, and filter. So based on this, we can take permit, deny, redirect, and copy, depending on what you want. Based on this, let's think about a couple of use cases. The first use case is you have two different EPGs, ESGs, or external EPGs. You can create a contract between them, which means you can redirect traffic between two EPGs, ESGs, or external EPGs. That's the general use case. The second use case is even between EPGs, ESGs in the same bridge domain, same subnet, we can apply contract. That's the beauty of ACI, which means you can redirect traffic even between endpoints in the same subnet. Thinking about the traditional network, it might be pretty hard. Even between endpoints in the same EPG, ESG, we have intra-EPG, intra-ESG contract, which means we can redirect traffic even between endpoints in the same EPG, ESG. So these are the common PBR use cases. Let's double-click what sort of other use cases we can think of. It's based on source, destination, and filter. So as long as either one of them is different, you can take different action. So one common use case that you might like is inspect specific traffic. Let's say you have ESG1 and ESG2 having a contract between. You want TCP traffic to be inspected by firewall, but you just want to permit that traffic, other traffic. Then you can create two contract subjects. First one is redirect TCP, and then second one is permit IP. Then you can inspect specific TCP traffic only instead of redirecting all of the traffic to the firewall. That might be useful if you want to utilize firewall resources, because if you rely on routing for firewall insertion, you're gonna exhaust firewall resources because all of the traffic needs to go through firewall. So that sort of specific traffic inspection might be useful. Another use case is use of different firewall based on source. Let's say you have shared external L3 out and some internal different security zones, such as EPG, ESGs. And then based on source EPG or ESG, you want to use different firewall. Then you can create two contracts. Contract one is between ESG1 and external EPG. The action is redirect traffic to firewall 1. And then contract 2 is between ESG2 and external EPG. And then you can take different action because source is different. The action is redirect traffic to firewall 2. The third example is load balancer. I've been talking about PBR for both directions, consumer to provider, and provider to consumer. Both are redirected to firewall. So this bidirectional redirection might be common for firewall, TCP optimizer, or IPS. But in the case of load balancer or some device that translate IP, you might not need bidirectional PBR. For example, in the case of load balancer, incoming traffic from client is coming to the VIP owned by the load balancer. So we don't need to redirect because it's coming to the VIP. But thinking about return traffic, if the load balancer does source NAT for incoming traffic, you don't need PBR. But in case there is no source NAT applied on the load balancer, we need to make sure the return traffic comes back to the same load balancer. You can use load balancer as a destination gateway, but if you want to keep ACI fabric as a gateway, you need a PBR for return traffic only. In that case, provider to consumer direction, you enable PBR. In summary, PBR can be applied both directions or either one of them. So these are the typical PBR use cases. Hope this makes sense. Then we have a similar action that is called copy. So in the case of copy, instead of redirecting original traffic, we just permit original traffic, but we create a copy of that traffic and send it out from one of the leaf interfaces. That is connected to some of the off-path IDS kind of tap devices. So if you have some sort of off-path devices, maybe this might be useful. This is also based on contract, so you can copy specific traffic based on source, destination, and filter. I hope you see some of the benefits of PBR. Then let's think about what's the minimum requirements to use PBR. We have two important requirements. First, ACI must be layer 3. ACI must be gateway. Specifically speaking, bridge domain must have subnet, SVI, because I'm going to talk about detail later, but PBR basically rely to destination MAC. That is kind of routing. So ACI fabric must be a router. That is a requirement. The second requirement is VRF must be enforced mode, because we need contract enforcement. So you cannot use unenforced mode to use PBR. Then you might be wondering what would be your option to permit everything kind of behavior. So we have VZ any and preferred group as a common approach. I would personally recommend VZ any instead of preferred group. So let me explain the reason why. VZ any is a collection of EPGs, ESG, and external EPGs in the VRF. So basically, everyone in the VRF belongs to VZ any. If you have some specific shared service provider that everyone needs to talk, instead of creating many to one contract, you can just create VZ any to specific provider EPG contract. That basically allow everyone talk to the specific provider EPG, which means you can enable redirect on this VZ any to EPG contract so that everyone who needs to talk to the specific provider, traffic will be inspected by firewall. So this is just one contract, simple. If you want permit everything in the VRF, you can even do VZ any to VZ any. So basically, VZ any is the consumer and also the provider for the contract that permit all of the inter-EPG traffic in the VRF. So basically, this is to permit everything. So instead of using unenforced mode, use of VZ any to VZ any permit would be preferred approach, because you can enable PBR to redirect all of the inter-EPG traffic in the VRF by just consuming one TCAM rule. So this is better in terms of configuration simplification and also TCAM consumption. So I hope you see some benefits of PBR and understand the basic requirement. Since we talked about contract and VZ any, so let me double-click how contract works. So let's start with permit contract. So let's say we have a contract 1 between ESG1 and ESG2, and each EPG ESG has unique ID that is called class ID. In this example, I'm going to use 29 and 10934. Sorry, these are busy slides. So if it's hard to see, please open up the document on your hand or please come close to me. So basically, if we have a permit contract between two EPGs, we're going to consume two zoning rules on the switch. Basically, from consumer to provider, 29 to 10934 permit, and vice versa. So this is a permit contract. And then enabling PBR by attaching service graph to the contract 1, we allocate service EPG class IDs for firewall interfaces. In this case, I'm going to use 2-arm firewalls, but you can use 1-arm. Then zoning rules will be updated. As you can see, we have 2 redirect action and 2 permit action. So let's take a look at what it means. So 29 to 10934, consumer to provider, action is redirect traffic to destination group 11 In this case, it's consumer side of firewall. Then after firewall processes the traffic comes back from the other side of firewall, that is 32 to 10934. That we don't need to redirect. It's going to be permit. Then the return traffic 10934 back to 29 is also redirect, but it's different destination group. In this case, it's the provider side of firewall. Then traffic comes back from 30 to 29. That is permit. So this zoning rule will be automatically updated based on service graph and the contract. In traditional network, you might need to deal with what's the access list, ingress, egress, complicated configuration. But in the case of ACI, it will be automatically done. So that's how zoning rule works. And I'm going to double-click some important consideration. As you can see here, this is based on source, destination, and the filter. As you can see, one of the zoning rules just use default permit any filter instead of the filter used in the contract. It's because 32 to the provider, our assumption is firewall already inspected traffic. So we don't have to care about the detailed filter in the fabric security. So to decrease the number of TCAM consumption, we just simply use default filter. But it might be causing some issue. So we have an option to use original filter from contract instead of default all. So default allow all is the initial default configuration, but there might be some use case you might need to create filters from contract. Here is a use case. Let's say you have a contract 1, redirect UDP for firewall 1. And then you have a contract between same VPG pair, but different contract actions such as redirecting TCP, firewall, and IPS. In that case, regardless UDP or TCP, the first action is redirect to firewall 1. But thinking about after that, that's going to be from 32 to 10934. That one you need to take different action depending on UDP or TCP. So if it's UDP, you want permit. For TCP, you need redirect. So we need to keep the default contract filter instead of default permit any contract. So in that sort of case, you need to enable this filter from contract option that is available at service graph template. Here is another useful command on the leaf switches regarding the aliveness of PBR destination. In this example, we have 2 PBR destinations, and both are up. For example, you have 2 on firewall, 11.1 and 12.1. In the case of ACI PBR, the service leaf that is directly connected to the PBR destination, they check the aliveness information using IPSLA. And then that service leaf gonna distribute the aliveness information to another leaf node in the fabric, so that the other leaf node doesn't have to check the IPSLA connectivity to each independent PBR destinations. So which is efficient. Another important part is we have object called health group. So what it does is if one of the members in the health group gets down, we stop using all of the members. The use case is imagine you have 2 interfaces on the firewall, and if one of them is down, you stop using the other side, because the other direction starts using the other interface, it's going to be black hole. So you need to configure health group accordingly, unless your firewall has some tracking interface feature. So that's important design consideration. Let's double-click two node service graph zoning rules. Let's say firewall and then load balancer. For firewall, we enable PBR for both directions. For load balancer, we use PBR for return direction only. And then we're going to use these class IDs. Then, consumer to provider direction, originally it's from consumer to VIP. 29 to 10937. The action is redirecting to firewall, consumer side of firewall. Then, from firewall, 32 back to VIP, you don't need to redirect, it's just permit. After that, load balancer to the provider EPG, the action is permit. Then the return traffic, provider to consumer, will be redirected to the load balancer. Then the VIP back to consumer will be redirected to firewall. Then finally, from firewall to the consumer, it's going to be permit. So these zoning rules will be updated accordingly. So if you see some unexpected behavior in the forwarding, I would recommend checking the zoning rules. If zoning rule doesn't make sense, I think there might be some issue on the configuration. Here is another important consideration, especially for load balancer. In the case of load balancer, it's most likely load balancer checks the aliveness information to the real provider servers. So we need to permit bidirectional traffic from load balancer to the provider. But as you can see, we have load balancer to the provider, but we don't have permit rule for the return direction. So by default, we don't have direct bidirectional permit rule between service EPG and the consumer provider. So if you need direct connectivity, we have an option called direct connect at service graph template. So by default, it's false to reduce TCAM zoning rule consumption. But if you need it, please enable this. Otherwise, you might see the traffic drop somewhere. So that's the zoning rule. So let's take a look at the forwarding. So let's say we have 1.1 consumer and 2.1 provider and 2 ARM mode firewall. I just use different leaf nodes and different bridge domains for the explanation purpose, but it can technically be under the same leaf, same bridge domain. So this is just an example. So let's say consumer sends traffic to the provider. Since the gateway of server is ACI fabric, destination MAC is ACI leaf. Then, depending on whether leaf 1 can resolve destination class ID or not, we have different behavior. But let's say the ingress leaf 1 doesn't know the destination, then traffic goes to spine proxy, and then spine knows where the destination 2.1 is located. Then traffic goes to the destination leaf 3. Here, we finally apply policy because consumer source EPG information is in the VXLAN header, and then the destination is a local endpoint. Leaf 3 can resolve both source and destination class ID, and then we know the action is redirect because we checked the zoning rule. When PBR policy is applied, the switch change the destination MAC and segment ID of destination MAC. That basically points firewall consumer side is the destination MAC. Without changing source or destination IP, we can just redirect the traffic. So that's how it works. Then traffic is forwarded to the consumer side of the firewall. One important forwarding tips is even if the destination PBR MAC is under leaf 3, this is always going to spine proxy. So this is what it is. So when you do some troubleshooting, you might be wondering why this is going to spine proxy, but I just want to let you know that this is how it works when we redirect traffic. After firewall routes and inspects traffic, let's say to reach the destination subnet, firewall uses the other interface. Then traffic comes back to leaf 2 and then going to leaf 3 because destination IP is still 2.1. Here, PBR policy is not applied again because source class is different. Firewall provider to provider is permit based on zoning rule. Then the return traffic is almost the same. And here is another important forwarding information. So leaf 3 sees the traffic from 1.1 via leaf 2, but 1.1 is actually under leaf 1. So we shouldn't run 1.1 from service leaf. So we automatically disable data plane IP running if traffic comes from service EPG where PBR is enabled. So that's how it works behind the scenes. So you don't have to disable it intentionally, but I just want to let you know that this is a special behavior to avoid issue for PBR. Then the return traffic 2.1 back to 1.1. Let's say in this case, ingress leaf 3 can apply PBR policy. This time, destination MAC is the provider side of firewall. Then traffic arrives on the provider side of the firewall. Then traffic comes back, and then it's forwarded to the destination leaf 1. And here we don't apply PBR policy again because source class is firewall consumer. Then we don't run 2.1 from this traffic because this is from service EPG. Then traffic finally comes back to the destination, 1.1. So this is end-to-end traffic flow, but just as an example. So where policy is applied depends on endpoint running status and contract configuration. So you might be wondering where we apply policy. So this is a kind of like a full list of where policy is applied. I'm not going to explain everything. You can find the detail in ACI contract guide. So depending on intra-VRF, inter-VRF, EPG to EPG, L3 out to L3 out, we apply policy on either ingress or egress leaf. That said, you might be wondering how ingress, egress leaf enforcement works. So let me give one example. Let's say you have a ESG to ESG contract. Then we have important indication called policy applied bit. So this is in VXLAN header. So let's say you have traffic from 1.1 to 2.1. If ingress leaf 1 can resolve the destination class ID, ingress leaf can apply policy, and then they put policy applied bit to 1. That indicates policy was already applied on ingress, so that the egress leaf 2 doesn't apply policy because policy applied bit is 1. So this is ingress enforcement. In the case of egress leaf enforcement, let's say ingress leaf doesn't know the destination class ID, then the ingress leaf needs to permit traffic. Policy applied bit is 0, so that the egress leaf needs to identify, egress leaf needs to apply policy. In that case, it's an egress enforcement. So when you do troubleshooting, especially for PBR, you might need to check ingress and egress contract behavior, depending on endpoint running status. Contract priority is also important when it comes to combination of different actions, such as redirect and permit. So I'm going to talk about this. Rule of thumb is more granular rule will win. For example, if you have EPG to EPG contract, that wins over with any to EPG, that wins over with any to with any. So more granular rule take precedence. Between actions, deny is the strongest. Redirect and permit, it depends on granular filter or not. And then between filters, more specific port compared to any or IP or TCP, so specific filter will win. So you might be wondering what these mean, so let me give 3 examples. Let's say you have new VRF, new network, and then you don't know what sort of security policy you need to apply initially. I think that happens often. Then you can create with any to with any contract to permit everything in the VRF. It's gonna be 1020 permit contract. This is priority 17. By just using this one zoning rule, all of the inter-EPG traffic within the VRF will be permitted. So that's the situation number 1. And then you want TCP traffic redirected and inspected. Then you're going to create another contract or contract subject for with any to with any. Then it's going to add additional zoning rule. As you can see here, we have 020 redirect. The difference is filter. In this example, 74 is IP, 14 is TCP. Both are same priorities, but different filter. Specific filter will win. So here is a quiz. What's going to happen for TCP traffic between ESG1 and ESG2? It's going to be redirect because TCP filter is more specific, even though the zoning rule priorities are same. Then ESG1 to ESG2 UDP, it doesn't hit TCP redirect, but it still hits permit IP. So it's going to be permit. So this is what I meant by more granular filter win. Then the third use case is, let's say you have with any to with any permit, and you have north-south firewall inspection, with any to external EPG redirect, so that everyone who talks to external traffic is redirected. Then you have some specific east or west combination to be inspected. Then you create ESG1 to ESG redirect to TCP. Then what's going to happen for ESG1 to ESG2 TCP traffic? It's going to be redirect because ESG1 to ESG2 is more specific contract. Then ESG1 to external EPG. That's going to hit with any to external EPG contract. This is also redirect. If you have ESG1 to ESG2 UDP traffic, it still hits permit with any to with any. So this is how zoning rule priority works. Granular rule will always take precedence. This is just for your information. These are the zoning rule output of the previous example. ESG to ESG, priority 7. With any to EPG, priority 13 or 14. With any to with any is priority 17. The smaller number will actually stronger. So ESG to ESG wins over with any to ESG. That wins over with any to with any. So if you're going to have a little bit complicated combination of permit, redirect, deny, and if it doesn't work as you expect, please do take a look at the zoning rules and think about the priorities. So that's the zoning rule deep dive. So let's take a look at what's the commonly asked design questions. The first question is, which is better, 1-arm or 2-arm? So I usually say it depends on your preference and use case. Let me explain the reason why. So one num is good in terms of routing design simplification. You just want to need one interface, one static route, done. So you don't have to deal with routing configuration on the firewall that much. And this is actually the requirement if you have multiple EPGs, ESGs in the same subnet. Because if it's coming and going out from and to the same subnet, we cannot do two-arm firewall because firewall routing table cannot handle it. So if you have app-centric kind of behavior, it's most likely you need one-arm firewall. That said, your security team might not like it because they might use different interface for different security zone, security level. And also by default, Cisco ASA FTD doesn't allow intra-interface traffic, although this is configurable. So in that case, if security team doesn't like it, you have to use different interfaces, then two-arm might be better. But you need to deal with static route accordingly. If you misconfigure routing on firewall, probably it doesn't work. So this is the commonly asked question. It depends. The second question is, can we reuse the same PBR destinations multiple times? The answer is yes. And I'm going to explain two examples. First example is contract having multiple provider EPGs and multiple consumer EPGs. Then action is the same, using the same PBR destination, same firewall. Another example is even you have multiple different contracts, you can use the same PBR destination. So you don't have to create new service graph or new PBR destinations instantiating firewalls for all of the contract. So reusing PBR destination might be a practical approach. So that's possible. But two important design considerations. If you have so many provider EPGs and another many EPGs, I wouldn't recommend many-to-many EPG contract because it's going to potentially exhaust TCAM. If you have 100 EPGs and 100 EPGs, it's going to be roughly 10K. Instead, VZNE to VZNE PBR can allow us to redirect all of the traffic by just consuming one zoning rule. So if your majority of traffic needs to be inspected, I would recommend VZNE. And the second important design consideration is ACI fabric can redirect traffic, but the device, such as firewall, the routing design on the firewall, you need to do that accordingly. If they cannot handle it, end-to-end traffic doesn't work. So if you have complicated configuration, app-centric, having multiple EPGs, ESG combination, then use of one-arm firewall might be a practical option. Okay, the next question is, what types of devices can be PBR destinations? Initially, it must be L3 routed device. But after 5.0, L1, L2 inline transparent device can be also PBR destinations. And we can mix different types of PBR in the same service chain. For example, this contract between ESG1 and ESG2, we insert L1 inline IPS first, and then transparent L2 device, and then L3 device. So you can mix different types of devices in the same service chain. The last question is, can we use the same firewall for both north-south and east-west? So here's an example. You have a perimeter firewall connected to the fabric as an external router through L3 out. Then, for north-south traffic, you don't need a PBR. It's based on routing. At the same time, you want to use the same firewall interface for east-west. Then the PBR destination is in an L3 out instead of bridge domain. Originally, the PBR destination must be in a BD, but we found out that's a valid use case, so we added the support PBR destination in an L3 out. Here is the configuration example. You have east-west contract using PBR destination in an L3 out. And then for north-south, you can just create a contract, permit contract, without redirect between external EPG and internal EPG, so that firewall is inserted based on routing. At the same time, you're going to use this PBR destination for east-west contract. So let's take a look at the advanced use cases. I'm going to talk about two use cases. First one is inter-tenant contract with PBR. This might be possible if, let's say, if you have some shared external L3 out or shared services that is consumed by another different tenants. I'm going to use 3 examples. And then high availability design options, such as active standby firewall, active-active cluster, and independent active nodes with symmetric PBR. So let's take a look at the inter-VRF, inter-tenant contract with PBR. So what sort of configuration objects we need to deal with? First of all, we have contract, and then contract must be in the provider or common tenant. That's not specific to PBR. Whenever you have inter-tenant contract, you need to define contract in the provider or common tenant. And then service graph template that is attached to the contract, then this also needs to be in the same tenant, meaning provider or common tenant. Then L4, L7 device and device selection policies are the PBR configuration. L4, L7 device can be exported to another tenant. So as long as it's exported, it doesn't matter original location. The device selection policy is how to define which device we need to use for which service graph. It's based on contract name, graph name, and node name. For example, if we apply service graph 1 to contract 1, we're going to use ASA, for example. So it's based on contract name and the graph name on the node name. And as part of device selection policy, we select which segment we're going to put this firewall interfaces in, which BD or L3 out. So device selection policy needs to be able to see the contract, service graph, and network constructs. So important consideration is related to device selection policy. Device selection policy must be in the provider tenant. That actually we cannot change. It must be in the provider tenant. And then from device selection policy, we need to select L4, L7 device, service graph template, and network constructs. So you might be wondering what it means. So let me explain 3 examples. Let's say you have common tenant as a provider, user tenant as a consumer. In that case, you have a contract in the common provider tenant, and the service graph template is also in the common provider tenant. Then the device and device selection policies are in common tenant. From this device selection policy, if BD is in user tenant, it's not visible from common tenant. So the network configurations should be in common tenant. So this is example number 1. Example number 2 is, what if user tenant is a provider? In that case, user tenant has a contract because it's a provider, and then it's exported to common tenant so that common tenant EPG can consume the exported contract. Then the provider tenant has L47 device and device selection policy. In this case, BD can be either user tenant or common tenant, because if it's a common tenant, it's visible from the user tenant. If it's in the user tenant, since it's in the same tenant, it's visible from device selection policy. The last example is both are user tenants. Let's say user tenant 2 is the provider where contract, service graph template, and L47 device selection policy are configured. In that case, the BD must be in the provider tenant, because if it's in the other consumer user tenant 1, it's not visible from user tenant 2. So especially if it's between user tenant and another user tenant, you need to be careful which network you're going to use. So these are the considerations for inter-tenant PBR. HA design options, I'm going to talk about 3 options. First option is active standby cluster, or you can call it active standby HA. This might be common option. You have active device and standby device, and then they have shared IP. Active device takes care of the IP and the MAC of the shared IP 10.1.1 in this example. And then when standby switch over and elevated to the active role, then standby device gonna send ARP or GARP to get the ownership of IP and the MAC. So PBR perspective, it's one PBR destination IP, one logical device with 2 concrete devices. When switchover happens, it's actually not a PBR switchover, because PBR keeps sending traffic to the same IP, same MAC, but it's just an endpoint move from active location to new active location. The second example is active cluster. So each firewall vendor have slightly different approach. So in this presentation, I'm going to focus on Cisco ASA FTD approach, meaning all of the members in the cluster are active and using the same IP. So in this case, it's one PBR destination and one logical device and one concrete device. So I'm going to double click why it's one logical device instead of multiple devices in a couple of slides. The third use case is independent active nodes by using symmetric PBR. For example, you have 6 devices, 3 pairs, 3 IPs. In that case, we're going to load balance traffic across 3 IPs. From PBR configuration perspective, it's 3 PBR destinations per PBR policy and 1 logical device with 6 concrete devices. So these are the typical HA design options. Since active standby HA might be straightforward, so I'm going to double click active cluster and independent active nodes. So active cluster, I mentioned that it's one logical device. The reason is that if we connect them to fabric in different location, it means we run same IP from different location, that is flapping. So we must connect them as if it's one device. So instead of connecting them separately, you need to use one big port channel, so that we run 10.1.1 through this port channel 1, for example. That said, we have one exception in case of multi-port. In case of multi-port, it can be distributed as long as it's one location in port 1 and port 2. So as long as it's unique location per pod, you can distribute them. So to make this work, we have Anycast service feature available starting from 3.2. So what it does is each local service leaf runs a local endpoint, 10.1.1.1, and then it's going to notify spine that, oh, 10.1.1.1 is under myself. Then the spine runs the local location that is preferred, and then start exchanging the location information through BGP. Obviously, the local location is preferred because it's close, so that we can keep traffic locally as long as it's available. And then if local endpoint is all down, all of the members in the cluster are down in the local pod, then they start using the location in another pod, so that we can localize traffic, and also we can keep high availability. So I'm going to talk about the traffic path in a couple of slides in multi-location data center design discussion. Independent active nodes. So this is pretty useful if you want to scale out firewall. So imagine you have one firewall initially redirecting traffic. Then you see the amount of traffic has been increasing. Traditionally, you might need to buy big hardware and then replace it. But in case of symmetric PBR, you can just add another IPs, part of the same PBR group, so that based on hash, fabric is going to load balance traffic, keeping both incoming and return traffic going to the same firewall. So this is pretty useful if you want to scale out later. Because of the space, I put all of the firewalls under the same service leaf, but it can be distributed across multiple leaf nodes. So from high availability perspective, it might be making sense to distribute it, so that even if you have service leaf pair completely goes down, you can have another firewall available under another service leaf pair. So it's hash-based load balancing. By default, it's based on source IP, destination IP, and protocol number. But you might have a use case. Let's say you want same user, same IP, always go through the same device. In that case, you can use source IP only and destination IP-based hash. Here is an example. Let's say you have user 1 to 4, and then 4 PBR destinations. If you use source IP only based hash for the incoming traffic, left to right in this example, then if you use destination IP only for the return traffic, you can get same firewall selected for both incoming and return traffic, because source IP of incoming traffic is the destination IP of the return traffic. If we put the same value for hash calculation, we can get the same result, which means you can select the same PBR destination. The point here is that you can tweak this optional configuration, but you need to be careful, because now it's on your decision how to keep traffic symmetric. So if we have multiple PBR destinations, so what would happen if one of the PBR destinations is down? So we have a couple of options. By default, if we have 4 types of flows and 4 PBR destinations distributed nicely, orange goes to first one, blue goes to the second one, and so on. And then let's say the first device gets down, it's similar to port channel rehash. Instead of 4, now we have 3 active nodes, so all of the traffic will be rehashed. Of course, orange flow gets impacted, because now it goes to different firewall or device that doesn't have existing session. So it's most likely you need to re-establish connection. But not only orange, other flow could be impacted, because it could go to another fabric, another service device. So if you don't like it, we have an option called resilient hashing. So by using resilient hash, let's say first device is down, only orange flow will be redirected to another service device. But concern is that it's redirected to one of the available nodes. It's not something, let's say if you have multiple orange flows redistributed to 3 available nodes. It's not redistributed to 3 available nodes because orange just goes to one of the available nodes. So the concern is the second node in this example will get almost double the amount of traffic compared to steady state. So thinking about the capacity, you might need to set a limit in the steady state, let's say 40 or 50% of its capacity. That is not efficient. So if you don't like it, we have another additional option. That is backup PBR destination. So if you have backup device, that's not going to be used unless something happens. So in the steady state, it's going to primary PBR destinations. Then if one of the destination is down, then the traffic will be now redirected to backup node so that you don't have to think about 50% of limit in steady state. So I would say if you have more than 4 PBR destinations, probably the use of backup device might be more efficient. But it doesn't mean that I'm asking you to use resilient hashing always, because if you don't care about connection re-establishment because of your application, then probably default option, rehashing everything might be better in terms of traffic distribution. So it depends on your use case. So this is the last topic today, multi-location data center. So let me first explain what's the typical general challenge, regardless ACI or not. So imagine you have site 1, site 2, having independent active standby firewall in each site, and subnets are stretched. If traffic is coming in site 1, but the destination is in site 2, then it's most likely return traffic goes out through the local exit. Then that firewall doesn't know the initial connection, so it's most likely that firewall will drop the traffic because this is what stateful firewall is. So we need to keep traffic symmetric, especially if you have multi-location data centers using different firewalls. So I'm going to explain how ACI remote leaf multi-port multi-site can solve this challenge. So let's start with remote leaf. In the case of remote leaf, we have main location and remote location. Let's say you have a contract between ESG1, ESG2. So 2 important design considerations for remote leaf with service insertion. First of all, active standby service devices in the same service chain, they must be in the same location. So we cannot distribute them across main and remote location. That's a requirement and consideration, so that we don't have to think about asymmetric traffic because both are in the same site, same location. And the second design consideration, actually this is recommendation, is that VPC instead of open port is recommended to connect the firewall in the remote location. I'm going to explain reason in a couple of slides. Forwarding-wise, we have one unique behavior for remote leaf. Probably 30 or 40 minutes ago, I mentioned that it's always spine proxy for PBR. But it's not actually true for remote leaf after 4.0. Because if it's always spine proxy, traffic needs to go to the main location and comes back. That's not efficient. We don't like it. So we enable PBR locally instead of using spine proxy, so that we can eliminate unnecessary traffic hairpinning between main and remote location. That's actually the reason why we recommend VPC instead of open port. Imagine if you have open port, in this example, firewall is connected to firewall 2, and then connection to leaf 1 is disabled or standby. In that case, even though leaf 1 can locally redirect traffic, traffic needs to go to the upstream router and then comes back. That's not efficient. Of course, this could happen if one of the members in the VPC is down, but in steady state, if we can use VPC, that's even better because there's no traffic going to upstream router and then coming back. So that's the remote leaf design consideration. So multi-pod, we have 3 design options. Active standby across pods. In that case, we don't need to pay attention on asymmetric traffic because active device always takes care of the traffic. That's the simplest option. But the concern is traffic always needs to go to the pod where active device is located. So this is probably good if the location of 2 pods are close enough. The second option is active-active cluster across pods. So actually, this might be the best option, and I'm going to double-click this option. The third option is independent active device in each pod. So this is also good, but the concern is load balancing is based on hash. So there might be traffic hairpinning. For example, even traffic is within port 1, endpoint 1, endpoint 2 in port 1, based on hash, this could be redirected to a firewall in port 2, and then coming back. So I'm going to double-click the second option, because first and second option are actually common for multi-pod. So active-active cluster across pods, let's start with north-south, external EPG to internal EPG contract. You have external EPG in both pods, and the web EPGs in both pods, and then active-active cluster across pods. Thanks to Anycast service feature, spine in each pod prefers a local location. In the case of north-south, it's always compute leaf enforcement. PBR policy is applied on where destination endpoint is connected. And then that leaf in port 1 prefers the local location, so that traffic is localized instead of going to another pod. Even if the destination is in port 2 leaf gonna apply policy, and then that port 2 leaf prefers the local location. And then the return traffic will be also enforced by the same compute leaf, selecting the local PBR destination so that we can keep traffic symmetric and also localize traffic, which is great. And then even if all of the local firewalls are down, you still have firewalls in the remote pod. Of course, in that case, traffic is hairpinning, but you can still keep the traffic going. For east or west, Web 2 app, let's start with intra-pod traffic. If both source and destinations are in the same pod, regardless ingress or egress enforcement, local firewall will be used. And then within port 2, they're going to use firewall in port 2. So there is no traffic hairpinning. Traffic can be localized, and it's high available, which is great. One concern is inter-pod traffic, east or west. This could have asymmetric traffic, but thanks to active-active cluster, this will work. So let's say ingress leaf in port 1 redirects traffic. That goes to firewall in port 1. Then traffic is going to the destination in port 2. And then the return traffic, if it's also ingress enforcement, traffic could go to firewall in port 2. That is different. But thanks to active-active cluster, they are acting as if it's one logical device. They have some connection sync or something like this. In the case of Cisco ASA FTD, they have a control link to take care of traffic back to the original firewall that owns the session. Then traffic is working even if we have asymmetric traffic. So in summary, thanks to active-active cluster across pods, we can localize traffic as much as possible, and we have high availability. And even if we have asymmetric traffic, this should work thanks to one logical device across pods. So that's a multi-pod. So the last example is multi-site. In the case of multi-site, instead of first two options, we recommend the last option, independent device in each site, because the intention of multi-site is fault domain isolation. So it would make sense to have different fault domain from firewall perspective as well. It's actually the requirement to have independent firewall is in each site with PBR. So I'm going to explain how forwarding works. Let's start with north-south, external EPG to web EPG contract. Both are stretched, each site has firewall. We support intra-VRF north-south and inter-VRF north-south. One consideration is inter-VRF, L3 out must be the provider. It's because we assume it's always compute leaf enforcement, because if we do compute leaf enforcement, we can always redirect traffic to the same firewall where destination endpoint is located. So it's similar to what we just explained for multi-pod. Regardless where it's coming, traffic is always redirected by compute leaf, and then compute leaf gonna use the local firewall for both incoming and return traffic. So we can keep traffic symmetric. There is no unnecessary traffic hairpinning. For east or west, there is one challenge because, as we discussed probably 60 minutes ago, it's an ingress or egress enforcement depending on endpoint learning status. So we need to enforce policy on the same leaf for both incoming and return traffic. So our approach is we always apply policy on the provider leaf instead of consumer leaf, so that we always insert firewall in provider side for both incoming and return traffic. But imagine provider to consumer direction. Provider leaf might not know the consumer endpoint information. Consumer to provider, this direction is fine because consumer class ID information is in the VXLAN header. But the provider to consumer direction, if provider leaf doesn't know the consumer EPG class ID, the provider leaf cannot apply policy. So we mandate consumer EPG subnet configuration to make this work. Otherwise, we cannot guarantee the provider leaf can always resolve consumer class ID. So this is one big consideration. And then it will be massaged in the next release. So I'm going to explain the detail later. But today, for east or west, we need to configure consumer EPG subnet. You might be wondering how we ensure the provider leaf enforcement. Because consumer leaf for this direction, consumer leaf could apply policy. But we need to bypass the consumer leaf enforcement. So we have special behavior for multi-site, EPG to EPG, consumer provider direction. So I'm going to double click just for your information. So let's say we have these class IDs. As you can see, consumer to provider, provider to consumer, we have redirect actions. But consumer to provider, we have new action, redirect override. So this is a new behavior. So what it does is, if destination endpoint is not a local endpoint, that leaf doesn't apply policy. It means, imagine you are the ingress leaf, consumer leaf, where endpoint is connected for web, Even if ingress leaf can resolve destination class ID, the destination endpoint is not local in this consumer leaf. So policy is not applied, policy applied bit is set to 0, then the destination provider leaf can apply policy. This is how we enforce provider leaf always apply policy, even if consumer leaf can resolve the destination. If both source and destinations are in the same site, it actually doesn't matter how to keep traffic symmetric because it's always go to the local PBR destination. If source and destination are under the same leaf, ingress leaf can apply policy because destination is local. So this is a special behavior for EPG to EPG multi-site. So this is what we support today. External EPG to EPG contract with PBR and EPG to EPG contract with PBR. Consumer EPG subnet is required. That's where we are today. And then the last 20 minutes, I'm going to spend explaining VZNE to VZNE, VZNE to EPG PBR in multi-site. That's been a very common ask. Many people have been waiting for this. So it will be coming finally. And it's going to be NDO 4.2 and ACI 603. It will be available in a couple of months. So we're going to also support L3 out to L3 out, but I'm going to talk about VZNE to EPG and VZNE to VZNE. So let's start with VZNE to EPG PBR in multi-site. So we have two challenges. How to keep traffic symmetric. This, we also use provider leaf enforcement similar to EPG to EPG. And the second challenge is how we can ensure the provider leaf can always resolve the destination consumer class ID without EPG subnet. Because if it's just EPG to EPG, you can potentially just configure consumer EPG subnet. But if it's VZNE, we don't want to configure all of the EPG subnets. And also, it's not good for application-centric approach. So for this, we have conversational learning. That is a new behavior. So I'm going to explain how it works. So imagine you have VZNE to app provider EPG configuration with PBR. We have web endpoint to app endpoint. And then web endpoint is part of VZNE, so it's consumer. Then provider leaf apply policy, and then provider site firewall will be inserted. And then this is true for both consumer to provider and provider to consumer traffic, assuming provider leaf can resolve the consumer class ID for this provider to consumer direction. Then you might be wondering, what if provider leaf doesn't know the consumer endpoint class ID? Here we have a new behavior to make sure firewall in provider site is inserted. So what it does is, if provider leaf cannot resolve the destination class ID, we have no choice but to just permit traffic. Implicit permit traffic meaning policy was not applied, policy applied bit is 0. Then here is a new behavior. The destination leaf receiving inter-site traffic that hits VZNE to app redirect rule, but policy was not applied. Policy was supposed to be applied in the provider site. So we know that. So we redirect traffic back to the firewall in provider site so that we can ensure provider site firewall will be inserted for both incoming and return traffic. Then after that, firewall gonna send traffic to the destination. So this is how we ensure provider site firewall is always inserted, even if provider leaf doesn't know the VZNE consumer endpoint. But this gonna be traffic hairpinning, which we don't like. So it's gonna happen at the very beginning only, thanks to conversational learning. So when provider leaf just implicitly permit traffic, the destination consumer leaf sends traffic back to the firewall inside 2. At the same time, they generate, the destination consumer leaf generates special control packet. Source is 1.1, destination is 2.1. So we flip the IP. Then the destination, which is provider leaf, receive that special packet that gets the provider leaf run 1.1, so that the remaining traffic is not going to be traffic hairpinning because provider leaf now apply policy because consumer endpoint is resolved on the provider leaf. So in a nutshell, even if provider leaf doesn't know the destination, initial couple of packets will be traffic hairpinning, but after the conversational learning, there is no unnecessary traffic hairpinning thanks to conversational learning. So this is how we ensure WithAny2 EPG PBR works with provider-side enforcement. So this is WithAny2 EPG PBR. And then the last topic is WithAny2 WithAny PBR. So that's basically redirect all of the inter-EPG traffic, regardless it's intra-site or inter-site. So we still have two same challenges, how to keep traffic symmetric and how to ensure ingress leaf can always resolve the destination class ID. So we use same conversational learning for WithAny2 WithAny. But the first challenge, how to keep traffic symmetric, is actually more challenging because in the case of WithAny2 WithAny, there is no notion of consumer-provider direction because WithAny is a consumer and the provider. So we come up with new approach. Instead of redirecting once, if it's inter-site traffic, we insert firewall in both sites, so that both of the firewall see both of the traffic directions. One important thing is, if it's intra-site traffic, you can just use firewall in that site. If it's inter-site traffic, we redirect traffic twice. So probably it's very hard to imagine, so I'm going to explain how it works. So let's say you have WithAny2 WithAny contract with PBR, multi-site, and you have a web endpoint in site 1, app endpoint in site 2. Each site has independent firewall. It's always ingress enforcement, and then the switches in site 1 always prefer firewall in site 1. So firewall 1 is inserted, then traffic goes to the destination. Here we have a new behavior. If it hits WithAny2 WithAny, and if traffic is from inter-site, and then firewall is already inserted in the source site, we redirect traffic again to insert firewall in the destination site as well. So we redirect traffic twice for both incoming and return traffic, so that since both firewalls see both incoming and return traffic, firewalls should permit traffic. After firewall inside 2 inspects traffic, that traffic is not redirected back again because it's intra-site traffic. So the criteria is, if traffic is from another site, if firewall was already inserted, we redirect traffic again in the destination site. For return traffic, it's same. We enable PBR for both incoming and return traffic. So you might be wondering how we can kick the redirection again in the destination site. So we actually use policy applied bit to identify whether service was already inserted in the source site or not. So let me recap what policy applied bit is. So let's say you have EPG1, EPG2. If leaf 1 applies policy applied bit is set to 1, then the egress leaf can identify policy was already applied. So that's the indication if policy was applied or not. So we talked about the policy applied bit 1 and the policy applied bit 0. But we actually have 2 bits for policy applied bit. So we have been using both bits are 1, it's policy applied bit 1, meaning ingress leaf was already applied the policy. And if it's 0 and 0, ingress leaf didn't apply policy. Since we have 2 bits, we have new indication. So we're going to use SP equal 1, DP equal 0. That's set if traffic is from service EPG. So that we can use this indication to identify if firewall was already inserted or not. So let me apply this to the packet walk. So the first ingress leaf redirect traffic to firewall 1. When traffic comes back from firewall 1, since this traffic is from service EPG, we use SP equal 1 and DP equal 0. So that's a new indication so that the destination leaf can identify firewall was already inserted from source site. And this is from inter-site traffic. And then this hits VGNE to VGNE rule. So that the destination leaf can identify, okay, we got to enable PBR again because source site was already enforcing the PBR policy. And this is from inter-site. So traffic is redirected again. And then when traffic comes back, since this is also from service EPG, we have this SP equal 1, DP equal 0. But we don't redirect traffic again because it's intra-site traffic. So the criteria for this redirect again kind of action, we have 2 requirements. One is SP equal 1, DP equal 0. Traffic is coming from service EPG. And the second criteria is traffic is from different site. If it's intra-site, no redirection again. Only when it's from inter-site and service EPG was inserted from the other site, we insert traffic to firewall 2. So this is a new behavior only for VGNE to VGNE. For return traffic, it's same. Site 2 leaf redirect traffic to site 2 firewall. When traffic comes back, we have that special new indication set if it's traffic from service EPG. Then the destination leaf in site 1 sees the traffic from site 2, inter-site traffic, with this new indication, SP equal 1, DP equal 0. So we redirect traffic again, and then when traffic comes back from the local firewall, we don't enable redirect again because it's intra-site traffic. So this is how VGNE to VGNE inter-site works. But I just want to let you know that this is happening behind the scene, so you don't have to pay attention on the configuration. It will be working without knowing that. And even we have this redirecting twice kind of behavior. As I mentioned in the beginning, intra-site traffic, we redirect traffic once. So this new behavior is applicable only when you have inter-site traffic. So some people might not like redirecting twice kind of behavior because it's going to consume firewall resources. But imagine, practically speaking, intra-site traffic might be the majority of your traffic. Inter-site might happen for some active case or some specific situation. But generally speaking, localizing traffic as much as possible within site might be a practical approach. So even if we have redirect twice kind of behavior, I think you don't have to pay too much attention, in my personal opinion. So I would like to spend a couple of slides for conversational learning and how to bypass firewall. So conversational learning is pretty much same with VGNE to EPG. if ingress leaf doesn't know the destination, then traffic is going to the destination leaf, and if policy was not applied, traffic gets back to the source firewall. And then, when traffic comes back from firewall, we have new indication so that traffic can be redirected to the local firewall in site 2. So this is how we can enforce firewall insertion on both source and destination sites, even though the destination endpoint is not resolved. At the same time, similar to VZNE2 EPG contract with PBR, we generate the special packet that gets source leaf run the destination endpoint. So similar to VZNE2 EPG, we might have some traffic hairpinning at the very beginning, but after conversational learning, you won't have unnecessary traffic hairpinning. So this is the firewall insertion. And then the last topic is, what if you want to bypass firewall? Because VZNE to VZNE PBR basically redirect all of the inter-EPG traffic in the VRF. But you might want to bypass some firewall. I'm going to talk about the 2 use cases. First use case is intra-EPG traffic. By default, actually you don't need to configure anything. By default, intra-EPG permit rule is priority 3. That wins over VZNE to VZNE priority 17. So without configuring anything, web endpoint to web endpoint inter-site traffic is just permitted. If ingress leaf can resolve the destination class ID, it's ingress enforcement. If not, policy applied bit is set to 0, and then egress leaf apply policy, that is permit. There is no conflict because intra-EPG permit wins over VZNE to VZNE because of priority. Another use case is you have some specific EPG to EPG combination that you don't need firewall. Then you can just create a specific EPG to EPG permit contract without PBR. That's been supported. And then EPG to EPG contract is a priority 7 that wins over VZNE to VZNE priority 17. So basically it's just permitted. Regardless ingress or egress enforcement, priority 7 wins over priority 17. So you can still use bypass action on top of VZNE PBR. And I just want to point out that there is no need for consumer EPG subnet configuration for both VZNE to VZNE and specific EPG to EPG permit. So you can do app-centric approach thanks to this VZNE PBR finally. And then it will be available in a couple of months. And then this is actually the last slide. So this summarizes what we're going to support in 603. We have VZNE to EPG, VZNE to L3 out, and L3 out to L3 out. We don't need consumer EPG subnet configuration, and you can bypass firewall by configuring a specific permit rule. And then you still need firewall in each site. And we still don't support ESG. So we are working on ESG support in multi-site, probably after this release. So conclusions. So this is actually last slide. I hope you understand what the PBR use case is, how it works, couple of design tips, and how to do troubleshooting by checking zoning rules. It's flexible. We can redirect specific traffic based on contract. We can redirect traffic even intra-subnet, intra-EPG ESG, any to any to EPG ESG. And we can scale easily. We can do symmetric PBR, resilient hashing, and PBR destination can be L1, L2, or L3. And it can be connected anywhere. And then this is applicable to multi-location data centers, and we have a way to keep traffic symmetric to make this work. Unfortunately, we don't have a time to take care of the configuration step and things. If you are interested in, please take a look at PBR white paper that has some detail. And I put some links And then that explains contract detail, PBR deep dive, and also multi-site, multi-pod design options. So that's all what I want to talk. So if you like the session, please fill out the survey. Put your comments, what do you want to hear next, and please give us feedback. And continue your education. We still have Wednesday and Thursday. If you need a PBR troubleshooting deep dive, we have a session on Wednesday. So that's all. Thank you for your time. So if you have a question, please come and find me or leave WebEx team space message. I apologize, I probably 1 minute or 2 minutes late. So thank you for your time. Enjoy your Cisco Live. Thank you.